infinitesimally small particle that makes up everything. The atom is made of even smaller particles called protons, neutrons, and electrons, all of which are so tiny we cannot even see them with the most powerful microscope. As a student of chemistry, you have probably spent many restless nights wondering how we know that these things, protons, neutrons, and electrons, even exist, right? Right? Today, we will be answering all of these burning questions as we explore the history of the atom. But to do this, first we need to travel back in time. That's a little too far back. Forward a bit. A little more. Stop. It's around 400 BC, and we're in ancient Greece. Democritus, also known as the laughing philosopher, because of his emphasis on the value of cheerfulness, is wondering what would happen if you took a piece of matter, like this anachronistic piece of aluminum foil, and you cut it in half. And then you cut it in half again. And again, and again, and again, and again, and again, and again. Democritus muses that eventually you'd get something that you could not cut anymore. Democritus gives his basic particle a name, atomos, which means indivisible. Now, there's nothing scientific about this. Democritus doesn't have any proof. This is just a thought Democritus has, and being a philosopher, he does a lot of thinking. Democritus comes up with the following ideas. All matter is made of indivisible particles called atomos, or atoms. There is a void, or empty space, between the atoms. The atoms are completely solid. The atoms are homogeneous, which means they don't have an internal structure or anything inside them. They're the same all the way through. Democritus also philosophizes that atoms vary in size, shape, and weight. These are all nice ideas, and though not exactly correct, Democritus is off to a good start. Unfortunately, Democritus's ideas will be rejected by the great philosopher Aristotle, who will consider the theory of atoms to be ridiculous. And years later, it will also be rejected by important people in the early Christian church, and since the church has so much influence, it will be over 2,000 years before anyone begins thinking about the atom seriously. Let's go back into the time machine. Fast forward to about 1808. John Dalton, an English chemist, is about to revive atomic theory. Unlike Democritus, Dalton will use the scientific method. He does many experiments looking at properties of gases and properties of compounds, and he looks at how elements combine during chemical reactions. And he comes to the conclusion that matter must be made of tiny elementary particles. Of course, because he cannot see them, he does not know exactly what these particles look like, but he imagines them as tiny round balls, like billiard balls. Dalton puts forth several postulates. Though some of them will turn out to be correct, future scientists will debunk others, but such is the nature of science. Here are some of the ideas that Dalton has. Matter is composed of very tiny or microscopic particles called atoms. Well, this one's correct. Atoms of an element are identical in size, shape, mass, and in other properties. Well, Mr. Dalton, this is not exactly correct. In the future, people will discover atoms of an element may be different in their masses, if they're isotopes of each other, same number of protons, different numbers of neutrons. An atom cannot be subdivided, created, nor destroyed. Nice idea, but also wrong. As we will see, future scientists will discover that the atom can be divided into a number of subatomic particles, such as the proton and neutron and electron. Years in the future, scientists will also discover that atoms can be changed into other atoms through radioactive decay and nuclear reactions. Atoms combine with each other in simple whole number ratios to form compounds. Close, but the ratios aren't always that simple. Take a look at this chemical formula, C12H22O11. You can't say 12 to 22 to 11 is simple, can you? In chemical reactions, atoms are combined, separated, and rearranged. Well, Mr. Dalton, you certainly got that one right. Dalton's billiard ball model will hold up for a good 100 years. Let's get back into the time machine. It's 1897 and we are in England in the lab of J.J. Thomson, who is doing some experiments with a newly discovered device called a cathode ray tube. Nobody's really sure what these cathode rays are made of, and Thomson really wants to find out. In one of his experiments, he decides to put negatively and positively charged plates on each side of the cathode ray tube when it is turned on. He finds that the cathode ray appears to be attracted by the positively charged plate and repelled by the negatively charged plate. He concludes that the cathode rays must be made of negatively charged particles. Thomson has discovered the electron. Thomson measures the mass of these particles, and he finds that they are very tiny, even tinier than the atom. He proposes that these tiny negative particles are actually part of the atom. Thomson reasons that since atoms have an overall neutral charge, and they do, there must be positive charges inside the atom to balance out the negative electrons. Thomson proposes the plum pudding model, where electrons are described as negative particles floating in a soup of positive charge. This is plum pudding, a British dessert dating back to the Middle Ages. I suppose Thomson's model reminded him of this, with electrons instead of raisins. Now let's move forward through time to 1909. Ernest Rutherford is a physicist from New Zealand and a former student of Thomson. He thinks it could be cool to bombard atoms with positively charged alpha particles, and he conducts what will soon become known as Rutherford's gold foil experiment. Rutherford aims a thin beam of these positively charged alpha particles at a very thin sheet of pure gold. He predicts that the particles will pass straight through the foil, since, according to the plum pudding model, the positive charge should be spread out all over the atom. But that's not what happens. Although most of these alpha particles pass straight through, a few are deflected, some very significantly, as if they have bounced off something. Rutherford concludes that the atom is mostly empty space, but it has a small, dense, positively charged center that is capable of deflecting positively charged particles that come close to it. Rutherford has discovered the nucleus. Rutherford ditches the plum pudding model and he proposes the planetary model of the atom. In this model, the atom is mostly empty space, but it has a nucleus in the center and electrons orbiting it like planets orbit the sun. This is definitely an improvement over Thomson's plum pudding model, but we're not quite there yet. Once again, into the future. It's 1913, a few years later, and we're in the office of Danish scientist Niels Bohr. Bohr is a student of Rutherford and is familiar with Rutherford's model, but there's something about it that just doesn't seem quite right. Bohr has spent a lot of time recently reading about quantum theory, and he gets some ideas. Bohr proposes that the electrons are always traveling in specific orbits or shells around the nucleus. Each of these orbits is a fixed distance from the nucleus, and each has a different energy level. The energy is lowest near the nucleus, and the energy increases as you move farther and farther from the nucleus. Electrons must be in one orbit or another. They can never be in between orbits. When an electron absorbs or gives off energy, such as light or heat, the electron will jump from a higher or lower orbit. Okay, this is all kind of weird, I know, but Bohr's model gave scientists a lot of insight into the periodic table and why it is the way it is. And it also paved the way for... Okay, let's go ahead a few years and see. It's 1926, and Erwin Schrödinger is making improvements on Bohr's theory. He's using a lot of complicated math and physics to better describe where exactly the electrons probably are. And I say probably because you can't really know for certain. Schrödinger and several other physicists like Werner Heisenberg and Max Born and Paul Dirac and others are beginning to think of the electron as both a wave and a particle. And the quantum mechanical model they are putting together is starting to look pretty strange. Fortunately, this stuff is beyond the scope of this course, but there's a lot of stuff we can understand using simpler atomic models, even if they aren't quite as accurate or mathematically complicated. Okay, one more stop before we go home. It's 1932, and we are here with James Chadwick, who has just discovered the neutron. And this completes our atom for the moment. Time to go back home. I hope our little journey through history has answered a few of your questions about how we know what's inside this tiny little fundamental building block of matter that makes up everything. It's taken us over 2,000 years to get here, and there's still a lot to learn. But what we've learned so far is pretty useful, as you will soon see.